Okay, well, welcome everyone. Thank you so much for joining us for this webinar, Heat Pumps, What Homeowners Need to Know. My name is Rachel Goodgall, and I'm the Government Affairs Manager for the Energy Efficiency Alliance. We're a nonprofit that works to champion efficiency as the foundation of a clean, just, and resilient energy economy. And we're very pleased to bring you this webinar in collaboration with the New Jersey Conservation Foundation. And we're also very pleased to welcome you, especially today, because it is the 1-year anniversary of the Inflation Reduction Act signing, which is the largest climate and clean energy investment in US history. And one of the many investments in the IRA, and our focus tonight, of course, is increasing heat pump use in homes around the country. And we are focusing on New Jersey tonight, but if you are joining us from out of state, you are also welcome. And the vast majority of the information shared here will be broadly applicable to at least the Northeast and Mid-Atlantic regions. So let's get started. Next slide, please. So first, just a quick refresh on why we're talking about heat pumps. And most of you are probably here for one of two main reasons: climate and health. So heat pumps are a great way to reduce greenhouse gas emissions from buildings. And a new state-by-state analysis from RMI estimates that in New Jersey, switching from natural gas to heat pump heating reduces greenhouse gas emissions by 1/3 in the first year and over 60% over the lifetime of the appliance as the grid becomes cleaner. Also, by removing on-site combustion of fossil fuels, heat pumps remove local air pollutants like particulate matter 2.5 and nitrogen oxides that can negatively impact health. And those benefits are even greater if you're switching away from fuel oil or propane, which are more polluting sources of fuel than natural gas. But you're probably here already because you're aware of these benefits. And you also know that actually switching your heating and cooling systems is a big project. So we are here to help you start thinking about how you can tackle that. And we have a great panel of experts who are going to take us through. Next slide, please. So I'm going to start by introducing our panelists. Bill Amin is principal of M&E Engineers, which is a building engineering firm based in Somerville that provides power and efficiency services to corporate, industrial, and institutional clients. He has 35 years of experience as a mechanical and electrical engineer and is also a climate reality leader and chair of the Somerset County Energy Council. Scott Nelson is the founder and president of Oceanside Service, Inc., which is an HVAC contracting firm based in Allenhurst that specializes in efficiency and serves residential and commercial customers. Scott has over 35 years of experience in the HVAC industry and is also active with New Jersey Sierra Club's 50x30 building electrification campaign. And Chris Wisniewski is the vice president of Integrate Comfort Systems, also known as ICS, which is an HVAC and indoor air quality firm based in Belleville that specializes in heat pumps and serves residential and commercial customers in the northern New Jersey and New York City markets. ICS has been electrifying homes of all sizes up to 20,000 square feet since 2004. And they often work with engineers on their most high-end projects. So our agenda for today, next slide, please, is that we're going to start with some brief panelist presentations. Bill is going to review heat pump fundamentals and cover the types of heat pumps and some terminology you may need to know. Scott will talk a little bit about the equipment selection process and take you through 2 examples of recent projects that his firm has done. And Chris will also speak further on equipment considerations and discuss another case study where the customer switched off of heating oil. Then we will have a panel discussion with some frequently asked questions that we think will be of interest to many of you. And after that, we will take audience questions. So please put your questions in the Q&A box at any time. If it's regarding a specific presentation or something somebody says in the first part of the panel discussion, feel free to note who it's for. And my colleagues Hannah and Katie will be collecting those and feeding us your questions. So we're excited to pose those to the panelists. And then we'll wrap up and send you on your evening. So with that, I'd like to turn it over to Bill for our first presentation.
Very good. Thank you, Rachel. Thanks everybody for attending. So I'm the engineer in the group, so I want to explain some fundamentals. Engineers like to use lots of jargon and terms that don't make any sense, so I'm trying to make some sense of that for everybody. So as Rachel said, I'm going to talk about some fundamentals, different types of heat pumps, and just some of the terminology, so that as you start to explore this, you have a better handle on what we're doing. So next slide, please. So a lot of people, and I can see both sides of this argument, whether a heat pump is a good name for what we're talking about, but it actually is a good name, because heat pumps use refrigerant to pump heat from one place to another. An air conditioner pumps heat from your house to the outside. A heat pump is the same exact thing. In fact, in many cases, it's the same unit with a reversing valve, and it does just the opposite. It pumps heat from the outside to the inside. And with we're going to talk about some of the newer units that are out in the market in the past few years. They can do that when you don't think there's any heat outside, because it's almost 0 degrees. There actually is heat outside, because that's in degrees Kelvin or something. It's like 300, 400 degrees. So there's still energy outside that can be put into your house. All of these bullets are numbered 1. That's not right. Anyway, the beautiful thing about a heat pump is that for the amount of energy we put in, we put energy into a compressor and a condenser fan. But for every unit of energy we put in, we can get 2, 3, or 4 units out, sometimes even more than that. So it's like free energy. You pay for 1 kilowatt hour, you're going to get 4 kilowatt hours of heat out of this unit. So it's incredibly efficient and economical, because you're taking free energy out of the atmosphere and putting it into your house. And the ratio of what we call the useful energy output to the input energy, is what you're paying for, is called the coefficient of performance, the COP. So this is a function of the machine design, but it's also a function of physics. So next slide, please. As I said, heat pumps are really no different than air conditioners, except they're working in reverse. And the COP is a function of the machine design, but it's also a function of thermodynamics, because it depends on the amount of lift. What's the temperature difference between where you're taking the heat to where you're putting the heat? So the lower the lift, the closer those temperatures are together, the greater the COP. This is called the Carnot cycle, and it's a matter of thermodynamics. We see, fairly typical temperatures that we deal with on heat pumps are, if it's 30 degrees out, we're trying to heat the house to 70. We have a 40-degree lift. In the air conditioner in the summer, it's generally got a 25-degree lift. So that's, and in these cases, that's when we're talking about a COP of around 4 times the energy output compared to the input. Next slide, please. In the past 10 years, I'd say, more and more manufacturers are offering cold climate heat pumps. So heat pumps that I've done heat pumps for 30 years, and the old air source heat pumps worked down to about 30 degrees, and after that they didn't work. You would need to use auxiliary heat, which would be either a gas furnace or another system, or electric resistance heat. And when they went to electric resistance heat, if that's the type of unit you had, you got whacked in December and January and February with some high electric bills. That's true. Not anymore. If you get a cold climate heat pump, there's numerous manufacturers that offer them with 100% heat capacity down to 5 degrees, and they continue to operate down to minus 13. So no auxiliary heat is really required. And even down at 5 degrees, they're still giving you a COP of 2. So you're still only paying for half of the energy that you're getting out of the unit. So these things are a really market transformation type of product. Next slide. As much as I love the cold climate heat pumps, I'm still a big fan of geothermal heat pumps. They tend to be more expensive because the equipment inside is pretty much the same, but you have to drill holes or somehow put piping in the ground and use the ground as your heat source. The beauty of that is you see now in the wintertime, the ground is 55 degrees. So we have lower lift, higher COPs. And also in the summer, we've got a nice cold source to reject to. Instead of trying to reject to 95 degrees, we're rejecting to 55 degrees. It's super efficient. And last but not least, next slide. Is an open loop geothermal system. And if you're in a rural area where if you run on well water, we've taken buildings that run on well water and we just run that well pump through the heat pump and put that water back into another well. So we just borrow it. We lower the temperature a little bit in the winter, raise the temperature a little bit in the summer. The COP on these units is outstanding. It's fantastic, and it's really not, if you've already got a well and you're already paying for that expense, it's really not any more expensive than a conventional unit. So those are some of the fundamentals. Happy to answer questions about others, but I think we're going to get into some case studies. So
yes, thank you so
take
much,
it away, Rachel.
Bill. Yeah, and we're going to hand it over to Scott.
Good evening, everyone. So what you see in front of you is a typical selection chart for building a VRF, variable refrigerant flow, or a VRV, variable refrigerant volume heat pump system for a house. This happens to be a project that we're going to be starting in the fall in Deal, and the selection charts, depending on what manufacturer you use, allows you to build a system to have multiple indoor evaporators to each piece of equipment. It'll let you know how many BTUs you have available as you build the system. If you look at this just shows a myriad of ductless wall heads and ducted units connected to multiple outdoor heat pump condensers. This is a cold climate, happens to be a carrier system that will give a little bit more than 100% of rated capacity down to 5 degrees. So there's a lot of science to go to Bill's engineering comments, a lot of science that goes into how you build this and how you design it. You have to make sure you have proper heat gain, heat loss done to the house to allow you to understand how to build the system. Next slide, please. So some things you need to be concerned with if you're thinking about retrofitting an existing house to a heat pump is a couple of things. Where a typical gas or fossil fuel fired appliance, there's some built-in extra capacity in that piece of equipment. So we don't necessarily need every BTU out of the max capabilities of that heating system to heat your house, because the driver for most fossil fuel forced air systems is the size of the air conditioning unit. So the CFM's cubic feet per minute of air that unit needs to deliver for the air conditioning needs tends to drive the heating BTUs of that fossil fuel appliance a little higher than necessary. So when you get to doing a heat pump, you need every BTU that a heat pump delivers. You're in most homes that are not spray foamed for insulation require twice the amount of BTUs to heat than it does to cool. And the problem with that when you're doing a retrofit to an existing house is that your air conditioning system's primary function is it's a dehumidification system that happens to drop temperature while it's removing the moisture out of your house. So when you design a heat pump system for that same house that had fossil fuel in it before, if we size that system too big, because we need those BTUs for heat, we don't, in the summertime, we run into the potential problem of not taking the moisture out of the air and dropping the temperature in the summer too quickly. So there has to be some science on how you do a home. So you need to know the envelope, you need to seal the envelope as best as possible. The duct system and most existing homes are all very leaky. Stuff that's built today, everything is mastic, which is a sealant device that goes around, sealant application that goes around all the duct connections. So you're keeping all of the air inside the duct system. So you're able to deliver 100% of the rated cubic feet per minute of air delivery you need for that particular system. If you don't do that, you'll wind up, when we get to those colder temperatures, this winter we didn't have much. We had a handful of days, maybe 3 or 4 that were below 10. But depending where you are in the state, you could have a lot of single-digit mornings, and you need to make sure that you're providing the proper amount of BTUs. So the slide pictures you see here, the one on the right, this is a house in the town where my business is in Allenhurst. Homeowner wanted to convert to all cold climate heat pump. We couldn't do that based on the envelope in the house. So the picture on the right is a garage studio apartment that has a dual fuel system, has a gas furnace in the attic, a heat pump condenser outside, and we create a balance point and throttle from the heat pump to the gas furnace when it gets below 20 degrees. Slides on the left, the slimline suitcase looking condenser is a straight heat pump that does the 3rd floor with some backup electric resistance heat. And the other 2 square condensers are also their inverter technology. All of those is one's a straight heat pump on the 2nd floor, and the 1st floor, which is always going to be the coldest area in your home, if it's a stacked home of multiple floors, utilizes a hot water coil from an existing boiler that has that does domestic hot water needs in the house as its backup heat below 25 degrees. So everybody's familiar with a hybrid car. Sometimes if your envelope in your house isn't what needs to be, a hybrid application gets you to, as low of a carbon footprint without having to sacrifice comfort in the house. Next slide, please. This is part of the same job. The 1st and 2nd floor had high velocity air conditioning. So this house, we took all the radiators out because they did not want them anymore. And we replaced the 2 high velocity air handlers, which is a high pressure duct system. Does a great job in utilizing a heat pump. It heats and cools via aspiration, creates a gentle vacuum effect inside the house. So that's what a high velocity air handler looks like, and they make them in straight air conditioning and heat pump application. Next slide, please. These are the 2nd and 3rd floor air handlers in that house. Same thing. The one on the left is the 3rd floor heat pump only. The one on the right is the high velocity, and the square rectangular box above it with the circuit breaker, that's the electric duct heater that helps it out when it gets below 25 degrees. Next slide. So this is a house in a town called West Long Branch in Monmouth County that did a fairly extensive renovation to it. Did a lot of resealing, new windows, got rid of all the fossil fuel. They wanted a straight cold climate heat pump. So this was actually installed by somebody else, and they did a terrible job. They could not heat the house because of delivery on a 50-degree day, let alone a 30-degree day. So my firm got called in to rectify it, and we redid the duct system to deliver the amount of BTUs that I spoke about earlier, that you need every BTU on a heat pump to heat your house properly. This house was ducted improperly. So we went through and ripped out everything that was done wrong and redid it. And the rest of the winter and all summer this year was really perfect for them. They were very, very happy, and really super low utility bills. Is there one more slide? Or is that it? Nope, that's it. So a couple of things you want to be concerned with before I hand this off is whatever you're used to for traditional air conditioning. And if you're thinking about switching and making a switch over to a cold climate heat pump, is that the compressors utilize inverter technology. So they're taking 208 or 230 volt AC current, depending on where you live, and they're converting it to three-phase DC current. And these compressors spin at a very high RPM, and they want to run at about 30% capacity. So you'll notice if you go to a system like this, it's going to run most of any given heating need day or cooling need day, but at a very, very slow speed. So you're really never going to feel the temperature in your house change even a 1/10 of 1 degree. It's the biggest energy usage on a central piece of air conditioning equipment or heat pump equipment is the start and the stop. Once it's on, by maintaining at a very, very low speed, it's kind of like using the cruise control feature in your car. Your car may have 300-400 horsepower depending on what you drive. If you're driving a gasoline powered car, you never need all of that. You only need about half of that on an everyday need. Same with your heating and cooling equipment. So when you utilize a inverter technology piece of equipment called climate heat pump, you're going to run that at very slow speed, kind of like using cruise control in your car. And it will kind of ramp up and ramp down based on the needs of the house. So it's going to take the outside temperature, it's going to take the temperature returning to the system, the temperature leaving the system, and it's going to modulate the compressor, the outdoor fan motor, and the indoor blower motor to all work in concert to run very, very slow, efficient, comfortable heating and air conditioning. But you have to get used to how it runs a little bit different than what you're used to. And if you're used to setting back your thermostat for when you're away from the house, you can still do that in the cooling side, but you're going to want to get away from that on the heating side, because the recovery on a heat pump, if you're setting that temperature back 4, 6, 8 degrees, when you're not there, it takes too long and you lose the benefit of anything you're saving by cycling it back. So just know you have to get kind of used to having a different mentality in how you operate your heating and cooling system when you go to an inverter heat pump. And that's it.
Thank you so much, Scott.
You're welcome.
Over to Chris.
Yeah, thank you very much. I'll touch on some different topics. I'll definitely build off of what Scott just said. Well, you could, I guess, find a slide for me, whatever the next slide is. We can skip that one. Next one. So one of the things I say, so we have a group right now here that's primarily concerned about efficiency and about the climate, but there's plenty of people, your neighbors, that are not. They don't really care much for that. And one of the features is that anytime we go to replace an air conditioning system or propose a new system, we do a little bit of education about heat pumps. And one of the main things that actually Scott was just talking about, that inverter technology where now your air conditioning acts like a dimmer switch or cruise control, is you get superior comfort in both AC and heating modes. And of course, you remove danger of carbon monoxide somewhere in your house when you have a burning device. And that usually attracts people to the conversation heat pumps, and people that weren't previously open to even knowing anything about heat pumps are kind of going, oh, you know what, this might make sense. So that's just that thought that, we try to talk about heat pumps with everybody. We can move to the next slide. I'm not sure what the next slide is. We can go past to the next slide as well. I think most people know about the dangers of carbon monoxide. So it's been said already, one of the most important things you have to do is you have to gauge how much capacity of heating and cooling you need in a house. And each house is going to be different. Houses built 10 years ago are a lot tighter than houses built 60 years ago. And what's important to note is if you visually kind of see that bar at the bottom where you have the cooling and the heating needs for the house, and Scott just said it, that a lot of homes are like twice the amount of BTUs you need to heat than you need to cool. So we find a lot of homes with a different range. Some are a little bit closer to each other, some are not, but 50-60% is what you're going to find of the cooling BTUs compared to the heating BTUs. So we need far more heating than we need cooling. So the challenge becomes now, how much heat pump do you want to do in your house? And usually that gets answered by how much budget you really want to spend. So you could easily change your AC unit to heat pump, but can it be sized to handle your entire heating needs? Probably not if you're just sticking with apples to apples. We can move on to the next slide. So, part of the heat pump project is really gauging, if you can go to the next slide, gauging, what kind of heat pump project do you want to do? Do you want to remove your current source of heating totally? Or do you want to put a heat pump in that is going to just offset a good amount of usage of your, let's just say, boiler or something else? Knowing that the majority of our heating season, we spend above 34, degrees, no matter what. The majority of our heating season is in the 30s, 40s, and 50s. So no matter what, if you get a heat pump and it's not a cold climate heat pump, and you do have another source of heat, I tell people you're still winning. You're still offsetting that carbon usage by, whatever amount that is, whether it's 50, 60, 70%, depending on the house. But if your desire is to go full heat pump, then there's a lot of considerations to be made. On top of it is choosing the right equipment, and what's called a cold weather heat pump. And if we go to the next slide, not all heat pumps are created equal. So this is something that I've used when trying to help homeowners, educate them against perhaps some competitor prices and competitors that are trying to propose something that we see is not quite correct. That every manufacturer has different performance curves, and it's very, very important to look at those. So we've mapped pretty much, a lot of them. This is just an example of one particular performance curve, but as you go to the left, it's the outdoor temperature getting colder. And as you can see, the very top line is the red line. That's a Mitsubishi Hyperheat unit. All the other units, manufacturers, when you down the bottom there, is when you start looking at their performance when it gets cold, they start putting out less heat, less heat, and less heat. So that's kind of important in the overall design, is that, sometimes the contractors that are proposing this stuff to you don't have quite the experience perhaps in dealing with full electrification and full heat pump and being, having a heat pump be your only primary source of heat. They sometimes look at the fact that, hey, we have 36,000 BTUs. Well, great. At what temperature? Because some of these units at 36,000 BTUs will put out 10,000 BTUs when it's 5 degrees out. And then this is your only source of heat. So that could be a problem. We can move on to the next slide. So, a lot of the solutions that we have is, if you don't have a great duct system, if you can't just replace your AC unit with a heat pump unit, apples for apples, and you need additional sort of heat around, especially a bigger house sometimes, you could do a mixture of having that ducted unit, having a couple ductless units and in certain spots to concentrate on the areas that need more heating than cooling. For instance, there's some 4-season sunroom type areas where some people say this is our winter hangout spot and we want to have it hot in here. Well, like the ducted system probably doesn't deliver what, in some houses anyway, doesn't deliver quite the amount of heat that it's supposed to. So you might add a, additional ductless system for that spot just to maintain that temperature. So there's lots of different solutions. There is no one size fits all. There is no like we have to stick with a ducted, and you could get very creative with it. We can go on to the next slide. I think we can skip this. I think it's been talked about, hybrid heat pumps were mentioned here. So, there's sometimes a good solution is going to be the fact that you do need that alternate source of heat. Just because you don't have quite enough heat pump for the house, or quite enough budget to get the second heat pump or whatever it is additional to it. But again, it's still okay because that secondary source of heat is not going to be used as the primary source of heat. The primary source of heat is going to be used 50, 60, 70% of the winter. We can go into the case study, I think, because a lot of this stuff has been sort of talked about. So we have a case study here. We have, it is a larger home, but you have to take this, I guess, with perspective, with a ratio for smaller homes. So we have a client that, had an 8 to 10,000 square foot house, something of that sort. They were paying $13,000 a year in oil. Oil boilers, it was quite an expense, of course. And we calculated exactly, what it came out to be and what he spent, and by, converting the numbers, he was definitely due to spend much money. The perfect storm about his air systems were also aging. So we can move on to the next slide. We replaced all of his AC systems with heat pumps. And we did exactly what I just talked about. We had to obviously replace some of his ducted units. We had to replace a lot of his ducts. A lot of homes have just poorly installed ductwork. And we did a mixture of various ductless units in spaces that needed additional heating. So that, we still had the proper cooling and we had the additional units for the extra heating that we needed. So it was a combination of all of that stuff. And if we go to the next slide here, the end result, which has proven itself sort of correct, we did an energy analysis, and basically, you remember that over that year they spent about 10,000. Well, we actually did the estimate. They spent $13,000 that one year that oil was higher, but they were spending about $11,000 a year before. But either way, if you take that $13,000 number a year in oil, it cost them, and it's hard to see probably at the lower right-hand corner, it cost them about $4,300 in heat pump heating. So we went from $13,000 oil to $4,400 in electric costs. So if we look at the projection here of a savings, this particular homeowner was saving $10,000 right off the first year. So we go to 10-year span, that's $100,000 that they were saving in utility bills. Now, granted, it's a larger residence, but if you take a residence that's, 1/4 the size, you can probably use those ratios. A lot of factors in this, of course, but this was a huge driving force for the homeowner. If a 15-year span, they would save $160,000. Pretty much the project paid for itself in that instance. So this was a no-brainer. And by the way, this is not anybody that was like-minded, like people probably on this, meeting here. There was zero consideration for the environment, zero consideration for even anything carbon offset. It was purely energy efficiency, money savings, driving force for the homeowner, and heat pumps managed to achieve that. That's it. I mean, I think everything else that I had to talk about is probably covered by Scott and Bill. Thank you.
Thanks so much, Chris. So I think the moral there is, if you are heating with oil, call Chris or Scott immediately and get switched to a heat pump. If you are heating with natural gas, there's more to consider about costs, etc. Obviously, still a lot of benefits, but if you're heating with oil, call immediately. Great, we're going to go into some panel discussion questions. And some of these have already been partially answered, but I'm going to start us off with a question that is often asked, which is, do heat pumps need supplemental heat in New Jersey? Is it possible to fully heat and cool your home with air source heat pumps? And we heard some case studies about this, but I'd love to just pose it to the panel again for quick answers. When somebody asks you that, what's your answer?
You want me to start?
Sure, great.
So we just recently did 2 houses, brand new from the ground up, with no no gas heat whatsoever, just straight cold climate heat pump. And both have been through 3 winters and have had no issue heating. In a new construction, it's very easy to do. In a retrofit application, once again, it depends on how tight the house is. You know, one of the things you want to concern yourself with if you're going to retrofit an existing house is making sure, you know, that your insulation is as good as it can be. That's really, you know, you want to keep the heat inside. You don't want it to go outside. And so that's really the driver. I just quoted a job last week from Stephen Pat Miller's organization. Was a recommendation from them, and they live in a townhouse, and they're in the middle. They're a middle unit, so they have insulation on both ends. People heating and cooling their houses on both sides, but we're a little shy on BTUs. So you know we do need some backup resistance heat or a hybrid application, dual fuel, to make that happen for them. So every house truly is case by case in retrofit. If you're doing new construction or adding a level to your home or putting an addition on, it's very easily done.
I can add a story. My son's house in Pennsylvania, 2-story colonial, oil heat. We sized the heat pumps for the heating. So it was a little expensive because the house had one furnace previously. We split it in and put it in, added a unit in the attic. And when we got down to that 0-degree weather last Christmas, I called him and said, "So how's your house?" He said, "It's fine." Why? He had no idea that this was even an issue. No auxiliary heat. Places work great, saving a lot of money.
Yeah, I'll just add to it. My last case study that I showed was all 100% heat pump. There's no other source of heat.
Great, thank you. And I'm going to bring in Barb Blumenthal from NJCF, New Jersey Conservation Foundation, who's co-hosting with me to ask him the next question.
Thank you. This was a wonderful introduction to this topic. I know there's a lot of people who are on a learning curve here, a lot of homeowners asking a lot of questions. So we've got some great, very knowledgeable people here. I work on these issues sort of with national experts and manufacturers and others. And one of the things that we've heard a lot from New England, where there are, as you know, hundreds of thousands of these units going in Maine, in Massachusetts, in New York, in places much colder than New Jersey. But the HVAC contractors, when we have these calls, always point out the customers come to them because they hear it's more comfortable. And I wonder if that's the big selling point when you're getting referrals. I mean, how does that work in New Jersey? Because that seems to be the #1 motivation for people to adopt these in the Northeast is improved comfort. So any thoughts about that?
I mean, Scott mentioned it, and I mentioned it. Inverter technology. When we do heat pumps, we don't do anything but inverters. Your basic for most people's basic furnaces are going to be 100% on, full blast heat, or off. You don't get that with inverter heat pumps. You basically have that dimmer switch effect where it can ramp up, ramp down, provide you the right temperature. First of all, when you get hot air coming out of a heat pump, it's not 120, 30 degrees. It's going to be 80, 90, some odd 100 degrees at best. So it's not terribly, hot, and there's no huge temperature difference. You don't have those huge swings. So absolutely, it's more comfortable. It's more comfortable because it's quieter too.
Yeah, and as I had mentioned, the thermostat, the indoor evaporator, whether it's a wall hung evaporator or a central high static air handler or a low medium static compartmentized air handler, all of that works in concert. So that thermostat that EEV valve, the electronic expansion valve, the inverter compressor, and the blower motor and the air handler all work in concert. So we're on a fossil fuel furnace, whether it be gas or oil or propane. They're moving that air through that duct system, at a pretty high speed. This is really just ramping up and down based on the needs of the home. So yes, it is much more comfortable and much quieter.
And we did
and
get oh, sorry, go ahead, Bill.
And the other, it depends on what type of indoor units you're using. But if you're using, the wall hung type units, you can create zoning that you could never do with a furnace before. You've got a south facing, west facing room. Each of those has its own thermostat, its own temperature control, and so you can control room by room, which you could never do with a furnace.
I was going to just follow up. Scott and Chris both mentioned that heat pumps are quieter, and we had several audience questions about noise or lack thereof. So I was wondering if you could just elaborate on the noise or
Sure.
lack thereof.
So, for example, an outdoor unit, if you're thinking of the noise that your outdoor condenser makes, some of them are noisier than others. Literally, you'd have to stand next to this thing or see the blades of grass or if there's a bush by it move to even know it's on, as far as outside noise is concerned. Inside noise, it's a variable speed blower motor, very, very slow start, ramps up to the needed RPMs to deliver the cubic feet per minute of air that the system needs to deliver. Generally runs at, once again, about 30% of capacity. And then when it does satisfy, same thing, it's a very slow stop. So it's inside and outside, it's literally whisper quiet.
So should we, Rachel, maybe I'll go to the next question. If you're a consumer, what kind of questions, you have to put yourself in the shoes of all these homeowners. What kind of questions should they be asking contractors when they're soliciting bids for this work?
Well, number one, you have to have a good gauge on the load of the house, the heating and cooling load. So you're going to rely on your contractor to do that. You should be asking them, how are they figuring out what size equipment they're putting in? That's one of the most first important steps. I mean, I don't care what equipment you pick. If it's not sized correctly, you're not going to have a good experience. So that's probably the most important question. The other one, for me, and I kind of said this before, is that we are pretty, I mean, you have a panel here of experts on heat pumps, Scott and Bill and all that, but heat pumps are a relatively new conversation in the state. The majority of contractors do not have a great experience, or they themselves don't even want to get involved in it. So you do have to ask them, how many times have you fully electrified a home? Have you ever done that? Because a lot of them will just tell you right away, no, you need an alternate source of heat. Heat pumps won't work. Well, if somebody tells you that, that means they don't really have experience in doing this. Doesn't mean they're bad contractors. They just don't have experience in doing this. So I think if you're truly serious about electrifying your whole house, you should ask them, how many times have you done this?
And to expand upon that, it's unfortunately there's not a lot of sharp knives in the drawer in our industry. The gray hair on my head is all of us are aging out of this industry. And when I broke into this 40 or so years ago, we were putting in heat pumps. As Monmouth and Ocean County expanded into the rural areas and they didn't have any natural gas services, people didn't want to heat with oil. We put heat pumps in. And then we took them all out because reciprocating compressor heat pumps, didn't work. People were tired of a 12 or 1,300 square foot house having $1,000 electric bill in the winter because of their electric resistance heat. Whether it was set up right or not, or the system was not sized properly. And now we're taking out fossil fuel systems and putting in heat pumps because of the advancement of technology. It's, to Chris's point, you have to find the right person to do it. And this can't be a dollar and cents driven purchase decision. because you do not ever in my industry, in Chris's industry, ever want to buy from the guy with the lowest price, because you're probably not getting the job that you're supposed to get. And it's, we've been doing this, since inverter technology came out. We've been putting heat pumps in, and because they're a great source of heating and cooling a house. It's unmatched comfort, unmatched indoor air quality. But if you're not asking the questions like Chris said, how many have you done? Do you know how to do a load calc? If you're doing it in an existing system, is my duct system big enough to deliver the BTUs? If it's not, all the costs that go into doing it is what drives up the number. And, as my participation in the 50 by 30 organization, people in farther north counties than mine, they'll call a contractor and they say, no, we don't do that, or you're wasting your money, or you need to have fossil fuel. And it's because they're uneducated in it, unfortunately. And there's too many. The bulk of our industry is guys that are 2, 3, 4, 5 trucks, or they're super big, 50 trucks. And there's not a lot of guys in between. So that maybe the bigger companies, or we're kind of a mid-size operation. We spend the time to train our staff and train ourselves to learn it. The smaller guys are working too much in their business instead of on their business to be able to offer the technology that's out there for everybody.
So I heard an answer that you have to ask the contractor about doing a load calc. There's something very specific, because consumers don't know what that means, what it looks like. I have been through this. I've had 5 different people come out, and they do the rule of thumb, yeah, you need this and this and this, but they didn't do a load calc. So what do you say when you really want to get a better answer from a contractor? What is it that consumers should be specifically asking for?
You want a heat loss, heat gain calculation of your home, which is, taking into consideration, the size of your windows, your doors, the square footage of your house, where the sun exposure is, the height of the ceilings, how the house is insulated, when it was built, all of those things. And
sometimes it's called a manual J.
Yep.
I mean, just so that people know what to ask for, because they wouldn't know any of that.
Yeah, ACA is the Air Conditioning Contractors of America. I actually sit on the board of directors of NJ ACA. I've been on the board of directors for 25 years, and it's part of a nationwide organization, which is best practices for our industry. And there's other companies that do load calcs, and you can fine tune them perfectly, or do block loads, depending on what you're trying to accomplish in your house, or what you're actually doing. But a heat loss, heat gain calculation is the only way to find out what your true needs are.
Barb, to your point, is that the question the homeowner should ask is, how are you going to do the heating and cooling calculations? And the only correct answers are ACA Manual J or the ASHRAE method. If they don't give you one of those answers, throw them out the door.
And it takes any of the guesswork out. Instead of, as you said, the rule of thumb method. It's just not the way to do it. It's Chris can speak to it as well. It's the only way to do it is the right way.
I have to say, I finally got somebody who just did it, and the size of the unit is half of what they thought it would be. So there's an upfront savings from the tonnage of the system that you think you're going to use.
Absolutely, because engineers and contractors both guilty of oversizing, because if you oversize the unit, you can never really get sued because you provided an adequate sized unit, but you haven't done the homeowner or the building owner any service by oversizing. So yeah, and they need to also, they need to look in your attic to see what kind of insulation you have. They need to study the house to see what type of windows you have, whether what what the construction is so that they enter the correct U values into those calculations.
I'm going to shift us to an audience question about cost. What can consumers expect in terms of upfront costs, and what are the variables in their homes that will contribute to what the cost is?
Well, that's a loaded question, right, Chris?
Yeah, I'm not sure you could really answer that. So many variables. I mean, 1,500 square foot house, we've done them from 10,000 to 50,000. It all, there's a lot of factors, including what a customer wants. I'm not sure I could answer that, but yeah, I mean, it could be the cost basically of replacing your AC. It could be that in some scenarios, but a little more. But quite often it's not. I mean, quite often the heat pump project is the more expensive project. Scott just mentioned that you should never go with the lowest price contractor, and we just mentioned all these things you have to do correctly, right, to get a successful project. So to do it correctly takes more effort, takes more knowledge, it just takes more. So in my opinion, you're always doing these projects because they make sense, they're affordable sometimes. So you do them to an affordability sort of budget. I do plenty of projects where we can propose to fix that ductwork that's not delivering air to the furthest room, but it may not be within a client's budget. So we scale it back, and the client understands that, hey, I'm going to have a pretty good house except for the room at the end. So everything gets tailored to the customer's sort of desires, and you know, as a good contractor, you have to tell them the expectations. I've been involved. Well, actually, I'm doing a project right now where the customers tell us the highest set point they have in heating mode is 60 degrees. They never heat their house higher than 60. And it came out perfect because our load calcs, actually, our heat pump was not going to be able to go pretty much higher than 62 degrees. So that came out perfect. But if you put another client in that same house, they're going to be like, we like our house at 70. So yeah, it's a loaded question. There's so many answers. There's not a good answer to this question, unless Scott, you can think of a better answer.
It really goes to what are we replacing? We're replacing a piece of equipment that's on a duct system put in the 60s that was only made to heat the house, or we're replacing a system that was put in the 90s, a duct system put in the 90s, which was made to put air conditioning and heat in the house. There really is no blanket answer to that, unfortunately. But it's going to be more than just changing out like for like, for sure.
So one thing we're seeing, there's a lot of questions coming in. They are great questions. We could be doing this for 2 or 3 hours. So one thing I'm going to commit for everybody who's listening is we're going to distill the information that's here, continue to, with these wonderful experts that we have, continue to elaborate on a Q&A document that we will post on websites. So there's a new CLEAN website. You may have heard the launch of a new collaborative effort from environmental groups called CLEAN, New Jersey Conservation, EEA. We're going to be posting this information that you're hearing, because people are kind of wanting you to repeat some things that you said before, but we're going to be able in the next month or so to get a lot of this Q&A follow-up questions answered for everybody and post it, because I know we're going to run out of time today.
Yes, we are going to run out of time. Let's see if we can take 1 or 2 more of these questions quickly. I see, is there a benefit to having a post-insulation blower door test to aid in sizing?
Yeah, absolutely. I mean, the blower door test is really going to be fine-tuned exactly what you need. I come into this scenario a lot of times when you have that really, really old house. I can tell the homeowner that getting an insulation project done here is probably going to move the needle in the sizing of equipment. And you should get it done first. Sometimes it's a pretty decently insulated house, and some insulation improvements could be made. And I tell them, listen, that probably will not move the needle in terms of sizing equipment. It's just going to save you on energy bills. So there's smaller insulation projects, bigger ones, but If you have a concern with your house and you're definitely looking to insulate it first, get it as tight as your budget allows you to get it, have a blower door test, and then we know exactly the sizing of the equipment.
Yeah, when we do heating calc, particularly less so on the cooling, the infiltration can be half the cost, and as much as engineers like to be very precise, the infiltration is kind of like a, we just guess at air changes per hour if we don't have a blower door test. So it's very, very useful.
Yeah, and having an energy audit done in your house is always something that's positive if you're thinking about doing this.
So Rachel, I think we should show the tax. People are asking about IRA benefits. Maybe we should do that, and then we can go over if there's interest in to keep going, but I want to make sure people have a chance to see that.
Sure, yes. Katie, if you have that document on deck, we'd love to share it, but if not, I will just let everyone know that we have we've put together a rundown of the federal tax credits, utility by utility heat pump incentives, and utility on-bill financing programs that can help you defer cost of a heat pump installation. And we will be sending that out to all attendees tomorrow because we knew we wouldn't have much time to talk about it, but we have that.
We can say a little bit, which is there's a 30% tax credit. So if you are, there's direct rebates for low and moderate income households. Low income households are getting $8,000 off the price of a heat pump installation, just off the top. And then there's direct rebates for electric panel upgrades, electric wiring, some weatherization. So there's up to $14,000 of direct rebates for low-income households. If you don't qualify for low and moderate income rebates, everybody qualifies for 30% off. So if you had a project that costs I'm going to throw a curveball here, a $7,000 project, 30% off is a savings of $2,100. There's an annual limit, it's $2,000 a year. So if you had a $14,000 project and it was done sort of around December and January, you can get $2,000 tax credits. You can get $4,000 off. So I think you're going to be seeing a lot of that, of people trying to do a project in pieces, even if it's October and March, but piecing out a project so that they can get the $2,000 off of a project, 30%, as they continue to upgrade their home. So I don't know if our colleagues here have thought about or heard anybody suggesting that yet.
The only thing you have to be cognizant of that the tax credit is if you owe tax. Yeah, you have to understand that, and you really should make sure you run any tax credit stuff past your tax advisor.
Yes.
Yes, absolutely. We are not giving accounting advice here. And I do want to just clarify that low income rebate program for heat pumps is upcoming. It is a federal program that states will administer, and the applications for states just opened. So New Jersey still has to design and create its program. So it's not available quite yet, but the tax credits are available right now. So I think, let me give one last real quick question. What is the lifespan of a heat pump system, air source cold climate heat pump?
Well,
Go ahead.
Go ahead, Chris. No, go ahead.
I was going to tell you, well, the good manufacturers like Mitsubishi, Daikin, they'll provide you 12 years parts warranty. So at least the manufacturers think it's going to be mostly trouble-free 12 years. The industry tells you well-maintained, you got to take care of it. It's got to be at least 15 years. It's a variable question. It's how well do you maintain it? I mean, we have systems that are past 20 years old and they're running perfectly. And we have systems that are, maybe haven't gotten the maintenance attention that have issues. But if it's well installed, well maintained, 15 to 25 year lifespan, I think is a decent lifespan that you can, and it will depend on the type of unit and the manufacturer as well.
With a heat pump, one of the things you have to make sure you do is make sure you clean your filters or replace them if they're replaceable ones, because it needs every BTU to heat that space. That's the key to having any type of heating and cooling equipment last longer. An average life of a traditional air conditioner is 12 to 15 years. Doesn't mean it can't last 30. Doesn't mean you want it to last 30, because, as we advance in this, what's really great about this industry is that the technology changes so quick that, what we think is awesome now will be antiquated, 5 or 6 years from now. But the cold climate, when the refrigerant changes, the type of refrigerants we use change, we're going to get a lot more cold climate opportunities for all the manufacturers. In the next couple of years, there'll be a lot more flooding the market, and a lot higher efficiencies. But you're running your central air at 12 to 15 years is running 3 to 4 months out of the year. This is running, maybe 10 months out of the year, 8 to 10 months, depending on where you live. And so, to know that 15 years is probably a good benchmark.
Great, thank you. Well, I want to thank our panelists, Chris, Scott, and Bill. Thank you so much for sharing your expertise with us. Barb, thank you for planning and hosting this with me. And thank you to all our attendees. As we said, we'll be sending out the information on the financing and incentives piece, and we will look to compile your questions and hope to answer some of those more in writing as well. So thank you so much. Have a great night, everyone.
Have a good night.
Thank you very much.
Thank you.